Hi, welcome to week 10. Let's get started. Here we go. There we are. So start off with some admin. Assignment 2. I'm sure many of you are deeply engrossed in assignment 2 at the moment. And there's just two major things I want to talk about. And that is, you've really got to be very careful about contribution statements. We design the grading system so that if someone can't contribute because they're sick or something like that, then the grading system takes care of that. But only if you fill out the contribution statements correctly. So if you're in hospital or something, then you put 0 contribution in your statement in your group mate, and you get compensated through the university's special consideration process, which will work just fine for you. Okay. Otherwise, your whole group suffers if you have something bad happen to you. Okay, so it's very, very important that you accurately fill out your contribution statements. Likewise, if you choose not to work very hard on the assignment and you're fine with someone else doing a lot of the work, that's okay, but you need to reflect that in your contribution statement. Okay, and so they need to have a higher contribution than you, and that needs to accurately reflect the fact that you didn't contribute as much. And it's incredibly important that you do that correctly. Okay. And again, we talk about integrity, and you really need to do this right. I've had reports from tutors that they're concerned about some groups and what's going on there. Please make sure you do the right thing. Make absolutely sure that you don't misrepresent someone else's work as your own, and also make sure you don't accidentally give someone else your assignment, or somehow or other your assignment ends up in someone else's hands. If that happens, you could be in very serious trouble. So it goes both ways. All right. I hate talking about this stuff, but I'm afraid I need to, and the tutors have again asked me to do that. Labs. There are no labs. In fact, there's no more labs except the last one where you do your presentation. Okay, so you're going to give a presentation at the end of semester, and that's the next lab. And also, there's no lecture this Friday. Now, does anyone have any questions on any of this? I don't see any questions on the stream. And the last thing is, for those of you who are at Friday's lecture, you'll know that about 45 minutes into the lecture, my internet cut out. Hopefully my internet's okay now, although no one has said anything on the Q&A, which has me slightly worried. I think I'm still, it looks like I'm still alive, which is great. But I didn't get any feedback that I'd gone offline, so I just kept talking, thinking that you all were still there, but no one was answering any questions. Make sure you answer the questions. I provided a link on Piazza to the 45-minute mark in the last lecture, and I encourage you to go through that, the last part of the lecture, and watch that in your own time. So now, any more admin questions? Okay, all good, great. Okay, now with that, we're ready to get on to the last part of the this section of the course, which is maps. This is as I said on Piazza for this week, this is an incredibly important part of the course. Why? I've said it a number of times, I'll say it again. This part brings together multiple dimensions of the course. You get to really nail down your understanding of container types, the Java container types, and what are the ones we're focused on? We're focused on lists, sets, and maps. We did them in, I think, J14, unit J14, I think it was. Let me have a quick look here. Let's bring that up just to remind everyone. Here we go. Yeah, J14 was collections, okay? And you may remember that one. We did an exercise where we had the class and we add student IDs and so forth into a map of students, and we also went and built Boggle. Okay, and Boggle used sets. I think it used lists, and I'm not sure if it used maps. I don't remember now, but it used collections to do the Boggle solution. Okay, so this is the pinnacle of all that, because in J14 I was teaching you how the Java collection types work. Okay. And are we meant to create a video yes, you are meant to create a video. I thought that was clear. Is that not clear? Someone's asking if you're supposed to do a contribution. And Brighton asks a really important question. She asks, is the contribution statement for stage G meant to reflect the overall contribution or only the stage G part? Well, what you need to understand is, what is stage G being assessed on? It's being assessed on pretty much the entire assignment. If you have a look at what stage G is in, and your contribution statement should reflect that. And I actually posted about that on Piazza just this week, just on last night, I think, on the weekly summary. So your last contribution statement really needs to reflect, as Leo has said on the chat there, it really needs to reflect the whole assignment. Okay, so if you want to get a strong mark in deliverable G, you can't just sort of suddenly start working in week 10. That's not going to get you there. When should you expect to see those marks? You should see them. They should be available soon. But if you haven't seen them, I just unfortunately the Brendan asked about when you're going to see marks. Unfortunately, the user interface is not awesome for doing the marks, and so I need to explicitly push them out. But also, your tutor needs to enter them. I will, after this lecture, go and push out whatever's in there. If you don't see them, so if you don't see them in an hour or so after this lecture, I will let you know. If you don't see them, then I will. Okay, so I got some bandwidth issues here. Yeah. All right. Sorry, guys. Someone's saying that they're buffering lots. I can see that at my end. Let me see what I can do. I don't think there's terribly much I can do. This is Australia's NBN, the broadband network for Australia. So sorry about that, folks. I'm not sure how much I can do about that. I'm just totally relying on whatever bandwidth I can get out of my house. I don't know why it should be particularly worse today than any other day. Frustrating. All right. I'm just thinking. I'm just trying to think if there's anything I can do that will improve my bandwidth, my upstream bandwidth. But I will. There's not much I can do, I don't think. I'll just do one thing. If you just bear with me. I'm just trying to fix something up here. All right. So I will forge ahead. I'm sorry for those of you who. So Griffith says he turned off low latency mode that stopped the buffering, but video cuts out intermittently. Audio is fine. Yeah, heaps of buffering. Sorry guys, I think the problem's at my end. I can see, or at least between me and Restream.io. So this stuff goes through a restreaming service, and I can see here that it's struggling to get it up upstreamed, and I have not the faintest idea why it would be doing that today. But I'm just going to have to forge ahead. If it completely drops out, I guess we'll do something else. Anyway, I'm just, for those of you who are not understanding what I'm talking about, I'm just responding to the chat here. A lot of people are saying they're having a lot of trouble with buffering, and I've got an indicator on my streaming device here which tells me that it's bad. So yeah. All right, let's go back to the lecture. I'm sorry about this. This is one of the things we have to live with a mediocre internet. Broadband internet in Australia, and COVID and remote lecturing. But if you can hear me, then great. And if my image is minimized, so hopefully it won't be demanding too much bandwidth. All right, let's move on. Actually, right now it's looking good again. So I don't know. Maybe something's fixed itself up. The mysteries of the internet. Let's refocus. Get back to the lecture. I'm going back to questions that people asked. Yeah, Brightney asked this really good question about the contribution statement. I think I've answered that. Your contribution statement needs to reflect all of the everything you did throughout the semester, because the G deliverable covers the whole thing. Someone asked about videos, presenting a video. You absolutely have to present a video. The instructions, I believe, are on the course webpage. If they're not, I will fix that. Now, has anyone else got any other questions? I think that's it. All right. Okay, so sorry, I got very distracted by all that. Let's get back to abstract data types. What we're talking about today is abstract data types, and we're talking about maps. And as I said a few minutes ago, the map is the pinnacle of the whole thing, because we looked at Java's container types in J14. I showed you that a second ago. Let's just go back. There it is, J14. And that showed you what Java gives you in terms of containers. Since then, in the A series, we've been looking at how those containers are implemented. And for each one of them, we implement them two different ways. We implemented the list two different ways, using array list and linked list. We implemented the set two different ways, using a hash set and a hash tree. And in doing so, we learnt a number of different things. Well, for the array list, you learned about arrays. You already knew about arrays. For the linked list, you learned how to do a linked list. for the hash set, we learned all about hash tables. You learned about hashing, and you learned about a hash table, and we used a hash table to implement the hash set. Okay, and then the next thing you learned was about trees. Okay, so we learned about trees, and we used trees to implement the tree set. Okay, now we're going to maps, and we're extending those ideas into maps. All right, so any questions on any of that? That's the big picture of what we've done and why we're here. Recap, we learned about containers. We also learned about abstract data types, and we learned about trees, linked lists, and hash tables. And they're the things we used to implement these container types. All right. All right, very good. And I can see that the streaming service seems stable now. Let's get on with this. So I've got a slide here to prompt me on all the stuff I just told you. The list, array list, linked list, set, hash set, BST set, and the map, the hash map, and the BST map. And we introduced hash tables and trees. All right. The map ADT is also, if you've programmed in other programming languages, you may have come across the maps as dictionaries or as associative arrays. They have different terminologies used in different places. But the key idea is that you have a key and a value and a storage indexed on the key. So you can put a key in there and you can get back a value. And if you go back to, let's have a look here. If you go back to, here we go. If we go back to J14, what we see in J14 is this is what we did in class before, and we created a bunch of students here. And then what we did is we put these students into a map, and the students were indexed using their UID. Why? Because the UID is a fixed value that uniquely identifies each student. And so we could use that as the key. The value was the whole student. So the key was the UID, the value was the student. Okay, and so we put these students into a map, and then we could do things like print out all the students in the map. We could pull a student out of the map by using, where is it? Let's just look through this code here. Okay, from the list. So there we go, we put the students in the map, and then we can do a get here, okay? So we look up this student here, that's the key, and then we do a get using that key, and that key there is the key for Bob, okay, because that's Bob's UID. So we look up the map, we get back a student, which is the value, and then we print out the name of that student, okay? So that was what we learned way back in J14, and that was the map container type. And remember, for each of Java's container types, there are different ways of implementing it, which have different trade-offs. We already looked at the different trade-offs involved with lists, with arrays, and with linked lists, and the pluses and minuses of using an array versus using a linked list. On the chat now, can anyone tell me what are the pluses and minuses of using a linked list versus using an array list? Using an array versus using a linked list. What's the pluses and minuses? Anyone on the chat there? And likewise, can anyone remember the pluses and minuses of using a tree versus using a hash map for sets? Okay, anyone there? All right, so now what we're going to do is we're going to look at this here. A map consists of key value pairs. I just explained that before, and I don't see any answers on the chat. Hopefully that doesn't mean you've just dropped off again. Like, there we go. I see some answers now. Great. Okay, so Adam says for linked list has fast insertion. Great, so we can add something quickly. Linked list, quick insertion of elements. Array list, quick accessing of any element, right? So we can grab something very fast out of an array, but it's hard to grow something in an array. It can be hard to grow something in an array because if you get to the end of the underlying array, you have to allocate a whole new array and move all the things from the old array into the new array. So resizing things is really annoying with an array list, but with a linked list, it's easy. Okay, so but array lists have a fast lookup, absolutely. All right, so as Linda said, yeah, linked lists are easy to expand or contract. And Harriet says a linked list, you have to search through the whole list to access something. That's absolutely right. So if I want to get to the third element, I've got to go 1, 2, 3 down the list to get to that third element, which is not a big deal. But if there's a million elements, I've got to go down a million elements until I get to that millionth element. So that's absolutely correct. Any other points? Okay, that's great. Now let's look at the hash map versus the hash tree. Okay, sorry. a hash set versus a BS tree set. Remember, the hash set used a hash table, and the BS tree set used a tree. Can anyone remember what the worst case is? What can go wrong with a hash set? Okay, a hash set. When can that go bad? Under what circumstances can a hash set go bad? Okay, that's my first question. Next question, so I'm looking for some answers on that. When can a hash set go bad? The next question is, when can a binary search tree go bad? Two key questions. When can a hash table go bad, and when can a binary search tree go bad? Remember that the hash tables that we looked at have a table which you hash into, and then a linked list. Okay, a hash table and a linked list. And the analogy we used when we built that was the one of finding the mail in a residential hall, the old snail mail, and that is we reduce the search time by using a hash. So instead of having all of things in one giant linked list, we have multiple linked lists, and we only have to search one fraction of the whole set. So the analogy with the mail was, instead of having one big pile for everyone's mail, we have 26 piles, one for each letter of the alphabet. So you're doing roughly 1/26 as much work when you go and look up for your letter in the mail. Okay, and the same basic analogy follows for a hash map. Now, what do people say here? Adam points out that a binary search tree can degenerate into a linked list. Yeah, if you have a binary search tree and by somehow or other everything goes onto one side of the tree, it actually ends up looking exactly like a linked list. The question is, how can that happen? Well, the answer is the way things are put into a binary search tree, unless you do something special, will be affected by the order in which they're added. And something really interesting is that if you add everything in an already sorted way, you'll end up everything going in a linked list. So if you add everything in increasing order, you'll have a linked list because you'll always keep adding things to the right. And if you always keep adding things to the right, you'll end up with, instead of a nice binary tree, everything will end up following the rightmost node, which basically looks exactly like a linked list. Conversely, if it's reverse sorted, everything will go on the left, and you'll have a binary search tree that looks exactly like a linked list going the other direction. Okay, and then Harriet says you can make it too big and the huge amount of space. Right, so there's this question about how do you size the table for a hash set. Okay, and we talked about the residential hall. If you had 200 students in the residential hall, you could make 200 pigeonholes. But that would, where I was, it was in the dining hall. If you had 200 pigeonholes, it would like fill the entire wall of the dining hall. Whereas if you have 26, hopefully you can see me now. This is extraordinarily frustrating. I really apologize for this. I thought I was going to get through this semester without this sort of ridiculous connectivity problem. Okay, it says I'm offline, but hopefully you can see me. Alright, I'm supposedly back, but my restream.io shows that I'm not back, so that's intensely frustrating. Sorry folks, I'm really apologize for this. No, Darren, the problem is the upstream, not the downstream. That's the issue here. Okay, so I want to know if you guys can see me live now. Unfortunately, I'm watching Restream.io and it's sorry, I'm looking at my streamer and it's telling me that I'm getting nothing and then I'm getting good connectivity. It's just going all over the place and I have no idea why. It just must be dropping a ton load of packets. I'm just going to try one more thing here, folks. I apologize for this. Okay. I believe it's back up. I just rebooted something. It's gone back to 0 again. All right, folks, just give me what I'm going to take a oops. All right, folks, sorry about all that. I'm back now, I believe. And we'll get on with this class. Right, so folks, what I'm going to do, for those of you who are here, okay. All right, I'm looking at the chat now. Two things. First of all, if this lecture cuts out again, I'm just going to go ahead, okay, and you'll just have to watch it later. That's the first thing. Second thing, I'm just going to answer some questions here. Go and upload the recording later. Yeah, no. Someone says the CI test for assignment 2. I don't know what you're talking about. I haven't updated the CI test for some time. I don't know. I'm wondering why you're asking that. And if you want to be more specific, I'll answer at the end of the lecture, but I don't know why you're asking about the CI test for assignment 2. They haven't changed in a little while as far as I know. With all that, I'm going to edit this video and edit all that rubbish out, all the stuff that just happened. And I'm just going to go back to this. I'm going to start this slide again because I certainly lost concentration. I expect you may have too. And like I said, I'm just going to forge ahead here and finish the lecture off regardless of what happens. Okay? Okay. All right. Let's move ahead. And I'm just gonna, as I say, I'm just gonna, from this point on, I'm just gonna go ahead regardless of whether or not the connection's there, and you'll just have to watch the recording. And I apologize for this. All I've done is reboot the various routers in the house, but the connection's still patchy, so there may be something outside of the house that's causing this. All right. So what we've got here in the map interface, we've got these methods here. This is like what we have in the Java collections type, but it's simpler, and this is what we'll be coding to in this class. Okay, and we've got a put. Now if you're on the chat, I'm going to ask you what does sorry, let me back up. What I wanted to say was, let's go back and look at the what we did here. Can anyone remember what we did in the previous class, where we did in J14, where we added elements? And if you remember rightly, I intentionally made a mistake, and I added the same one person with the same UID as another person. Can you remember what happened when I added a new person and I used an old person's UID? What actually happened was the new person replaced the old person. Okay, the new person replaced the old person. Let's see if I can run this. I'll try and run this now, just to remind you all. Run class list. Here it is. I'll make this bigger. It's going to run now. There it is. So you've got this group of people here, and I think the first time I add Sue is I get rid of one of the other people. So we've got 2, 4, 5 people there, and I must have fixed the bug. But if you go back and look, yeah, it overrides. Harriet's already answered the question on the chat there. It overrides. Okay, so the point is that when I add something with the same key as something that was already there, it overrides the one that was already there. And why is that? It's because the keys of a map need to be unique. Okay, and what's another way of saying that? Another way of saying that is the keys of a map form a set. So this is just like a set. The keys of a map form a set. All right, that is a very interesting insight if you think about that. Okay. Think about the fact that the keys of a map form a set. So, and what does a map consist of? It consists of key-value pairs. Now, if those keys form a set, then in principle, to build a map, all we need to do is to build a set of keys and then attach to each one a value. And the value could be an object. It's not necessarily a single thing like an integer. So it could be a student. So the keys is in this example here we've got on the screen, are a set of UIDs. And attached to each element of the set is a value, which is a student. Okay, so the keys form a set, and then we attach a value. This should be very, very helpful to you, because if you think about it, when we go and implement a map, all we need to do is to replay what we did when we built the sets and make one fairly minor change, which was, instead of answering the Boolean question, is this key in the set, or is this element in the set, yes, no, which is what a set does, we say, if it's in the set, please return, not a Boolean, yes, no, but rather please return the value that's associated with it. So all we need to do now is associate with each key a value, and when we ask for it, instead of saying yes, no, it's in there, we actually say, not only is it in there, but this is the value. Okay? So let's have a look at this at the interface. So the put corresponds to what in a set? So put has a key and a value as the arguments. And each one of these methods here has a direct analogy to sets. Okay, what does a put correspond to? Anyone? Can anyone say what a put corresponds to? A put corresponds to the add method in a set. Okay, in a set we add, like for example, we add a piece of fruit to that bowl. Okay, here we're not just adding a piece of fruit. Yeah, perfect. We're not just adding a piece of fruit, but we're adding a piece of fruit and a value. So if we're a fruit shop, we might have the piece of fruit and its price. Okay, so it might be a plum and it might be $7 a kilo. Okay, so instead of saying add plum, we say put plum $7 a kilo, right? And then get. So what's a get going to do? It corresponds directly to contains in a set. So contain says, is this thing in the set? Here, instead of saying that, we get back the value. So we say get plum, and then it will return $7. Okay, because the plums cost $7 a kilo, or whatever it is, right? So instead of returning a Boolean, yes, it's there or not, it returns the value. Okay, remove has a direct analogy. You just take the thing out of the map, just like you take the thing out of the set. And then size will tell us how many keys there are in the set, okay? And just like saying how many keys there are in the, how many keys there are in the map, which is just like what we do with the set. ToString is very similar, except that for each element, instead of just printing out the element, which is the key, we also have to print out the value. And normally we would do something like print them in parentheses. So you'd have a key and a value. Okay, just so otherwise it's very, very similar. So if you followed all of that, you'll now understand that building these maps, which is what we're going to do today, is actually remarkably similar to building the sets. Okay, remarkably similar. So now let's have a look here. This was the hash set that we looked at in the last lecture, right? You can remember how this is built up. The key idea here is the hash table, which sits there on the left. The hash table reduces the cost of the search, just like the pigeonholes for the mail in the residential hall. Okay, so we still have to search in a linked list. We're going to search that linked list of apple, banana, apricot, and cherry, but there are now 4 things in that linked list instead of 9, because there's 9 pieces of fruit in this particular example here, and we've reduced the search roughly by 1/4 because our hash table's got 4 entries in there. And in a perfect world, things would be evenly distributed, and the search would be about 1/4. Okay. And if the hash table had 1,000 entries, then the search might be reduced by a factor of 1,000, and so forth. Okay, so that's how it works. That's how the set works. Now, how does a map work? Well, at each node, not only do we have a key, like the apple, banana, or apricot, but we have a value. So in the case of a fruit shop, it might be the price per kilo of that particular kind of fruit. Okay, so we've got a key and a value. So this is it should be very obvious to you now that the relationship between a hash set and a hash map is very close. They are very closely related. All we're going to do is add a value instead of just adding a key. Now, the way I've illustrated it on this PowerPoint is as if they're 2 different things. In fact, we're going to have a single object, which is a key value pair. So at each node, we're going to have this key value pair object instead of a key. And I think that's at this point. Yeah. Oh, okay. Hang on. Let's go and demo this. Okay. So if we use this, and if we want to go and get something, the get operation, we get apricot. We do exactly the same thing we did with this set, but this time we find the value, which is 550, and we return that value. Okay, so that's the get operation for apricot. To do a put of a grape of 7, let's just go and do that again. So we're going to do a put of a grape, and it goes and searches. There is no grape, so it adds grape, and it has the value 7 and the key grape. Okay, so we added that whole node into the set because we added grape 7. We did a put of grape 7. Put orange. Now that's interesting. So orange was already in there. Okay, so we do a put of orange. Remember, if we did an add to a set of something that's already there, it has no effect. But if we do a put of something to a map, just like Harriet said a few minutes ago, it overrides what's already there. Okay, so in this case, orange had a price of $4. Now we've said put orange 350, and it says 350. Okay, I'll just do that again so you can see the animation. So we go in there, we find that orange is already there, and we add 350. If orange wasn't already there, then it would just add orange to the end. But orange was already there, so it changes the value. Okay? Likewise with a tree, same deal. So this is our tree that we built for the set. Now for the map, we just add values to each node in the tree. Okay? And we can do the same operations here. If we get the apricot, we do a search of the tree, just like we did for the set. But when we get to if we find it, instead of returning true to say that it contains it, we actually return the value that is held there, which in this case is 550. And then we do a put of grape of 7. Grape's not there, so we add a node, and we don't just add the key, which is grape, but we add the key and the value, which is grape and 7. And we do the orange, and again, orange is already in there, but we're putting a different value, so we change the value to 350. It was 4. Okay, and with that, we're ready for the mini quiz. And at this stage, it looks like my internet is holding up. And we're ready now to go and do implementation. What does get returned if the key is not in the map? Good question. We return null, okay? But, yeah, we return null is what we return. But that implies that the value can never be null, okay? Because otherwise you get confused, right? So if the key is not in the map, then we return the value null, which represents that we couldn't find it, okay? And with that, and to be honest with you, I don't remember right now what whether or not Java allows maps to have null values. Okay, to my mind, having a null value is just the same as having the thing not in the set. Okay, but the way we're going to implement it in class is that if the key is not in the map, then we return the value null. Okay, otherwise we return the value. Can I give an example of why you might need a key and a value for? Good question. Let's just go back to the PowerPoint. All right, so like this. Okay, so here we had a set of fruit. This slide that I'm showing you now is actually the slide we had way back a few weeks ago with sets. That is a set of fruit. Sets are useful things. We use sets in a few different things in our class. A set just tells you simply, does apple exist? And you can say yes, no, apple exists. It has no other information. We can only know if it exists or if it doesn't exist. What a map does is it can associate a value. Okay, we can say not only does the apple exist, but it has a price of $3.50, and we can have a ton load more information. I've made this incredibly simple, but just having the price. But I could have stuff like I could have like the provider. I could say, you know, we buy this apple from such and such farm or whatever it is, and it could have a whole lot of information in there. Or, you know, it could have a barcode, all kinds of stuff. Have a ton load of information. So whenever I look up apple, it could tell me everything we need to know about apples. Okay, with a set, it only returns one bit of information. We have apples or we don't have apples. With a map, we can return other information. We can return an entire object which can have all kinds of information in it. Okay, so maps are just like sets, but they're a lot more powerful because they can return an object instead of simply returning a Boolean, yes, we have it, or no, we don't have it. All right, so let's go ahead here. Where were we? I'll get rid of that. And what have we got in A6? Map. I've already gone and put the interface in there. All right, so I've gone and made this interface already for you to save typing in the class, and what you see here is exactly what was on the PowerPoint slide a minute ago. So here's a put, here's the remove, here's the key, and in answer to the question earlier about what if there's none, we return null. It says it quite clearly here. Size is the number of keys in the map, and then we've got a two-string. Do hash codes relate to key? Not necessarily, but we're going to use hash codes as we did. We used hash codes when we implemented trees. We use them to sort things, okay? But other than that, they don't have a relationship to it. We could use hash codes also, and we do use hash codes also for the hash map, okay? So we use hash codes. The keys hash code is quite useful to implement these things, okay? That's how it relates to the key. It relates to it because we can use the hash code to work out where to put the key in the table. Let's go back again to the PowerPoint. So it's a good question, okay? Got a question here about how does hash codes relate? Well, in this example I've put on the screen here, we've put the apple, banana, apricot, and cherry in this part because they start with letters A to F. This is a very, very naive example. In practice, when we implemented it in class, we didn't use the first letter of the object because the object could be any type. It's not necessarily a string. And this very simple example on the slide is actually a string. In general, it could be the key could be any object at all. It doesn't have to be a string. Here it's a string, doesn't have to be a string. And if it could be anything, the hash code is a nice way to work out which bucket to put it in. So we can put, you know, 1/4 of the things in this one, 1/4 in this one, and 1/4 in this one, probabilistically based on the hash code. Likewise, when we do the tree, we have to work out how to sort things in the tree. And we can use, in this example here that I showed on the PowerPoint, we sorted things in the tree according to the first letter of the string. So you see apple here, and then everything with a letter higher than APP in lexicographically goes to the right, which turns out everything is higher than that. Then you get to orange, and everything that's lower lexicographically to ORANGE goes on this side, and everything that's higher goes on this side. Okay, we're sorting it according to that string. But when we implement it in real life, that was just a very simplistic thing on the PowerPoint. What we did in real life was we used the hash code to do that. Okay, so we used hash codes. So hopefully that's answered your question about what hash codes have to do with keys. They're useful for sorting keys, and sorting keys is important. Let's go back to our code. So what we're going to do now is we're going to create an empty hash map and an empty binary search tree map, and then we'll create tests, and then we'll go and implement these things. And despite all those delays we had earlier with the internet, we should be able to do this on time, I think, with a bit of luck. Let's see how we go. So what we're going to do now is going to say new Java class, and we'll call it hash map, like that. And we want to add it to Git. And now what we're going to do is we're going to say we're going to add type parameters. Remember, this is generic. That's one of the many things that the this A series illustrates, is the use of generics. And what are we going to do here? Let's have a quick look at what we did for A5. I'm waiting for suggestions on the chat about what I should put in here. Let's have a quick look at what we did for the hash set. This is the set. We had T, which is the type of the element in the set. We could have renamed this E for element. We use T, which is often a default. What are we going to do for the hash map? Anyone know? Does anyone know what we're going to use for hash map? Well, the answer is here. I just showed it you actually a few minutes ago. We're going to use the key and the value. We've got two type parameters. Okay, two type parameters. And yeah, there we go. KV, perfect. Yep, great. Excellent. Okay, so those messages were a bit slow to come to me, but I see them all now. Great. So it's going to be like this. Exactly. And then what we're going to do here is going to say it extends a map KV, like that. Okay? And we're not going to extend Java util, but we're going to extend our own implementation like that. Whoops. K, comma, V, like that. Okay? And now what we're going to do is, of course, it's going to complain because we haven't implemented the methods, and we'll say, yeah, implement those methods for us, please. And it'll go and add all those methods for us. There they are. So we've got the empty implementations. All right. Perfect. Adam, thank you. I made the mistake again. Okay. It doesn't extend map, it implements map. Okay. So thank you for watching that and noticing my mistake. I said extends, which is inheritance, and Linda noticed also. I said extend, which is for inheritance, but actually this is an interface. We need to say implements. Okay, these are easy mistakes to make. I just made the mistake, and I think I made it in the last lecture too. All right, what we're going to do now is we're going to create another new class. It's going to be BSTMap, like that, and we're going to do the same stuff. We're going to give it two type parameters. One's going to be the key. One's going to be the value. Okay, because the key and the value could have different types. In the example on the PowerPoint slide, one was a string, the name of the fruit, and the other one was a number, the price. Okay, so there could be any two types. We don't know what they are. Implements map KV. K, comma V. All right, like that. And then it's going to ask us if we want to implement those things, and we'll say sure. And there they are. Okay, so we've gone and implemented them. And of course we've just got stubs there. All right. And put is void, remove is void, get returns null by default here, and size returns null. Okay, good question. Look, I was trying to tell you all that this is such an important lecture. Why is it important? Because it illustrates so many important concepts. It illustrates generics. Here we see generics with two type parameters, and it illustrates interfaces. Okay, and Adam noticed and Linda noticed I didn't do this right, but I fixed it now. Okay, it implements interfaces. Interfaces are really core concept in the class. An interface says that you are going to, it's a contract that says you're going to provide these methods. You can provide other methods. The example I gave you really early on in the class is the notion of a movable thing. The movable thing could be an airplane, it could be an elephant, and it could be, I see the connectivity's dropped off again, but I'm just going to forge ahead here, folks. It could be an elephant or whatever, okay? And all right, I'm just gonna forge ahead. I don't know if you can hear me or not, but I'm gonna forge ahead. All right, so an interface is a very important concept, and the map is in Java expressed as an interface. Likewise, the set was expressed as an interface, and likewise the list was an interface. And you see in IntelliJ draws it differently with a little I there, and down here we've got an I here. All right, and that tells us it's an interface, and And the whole idea of an interface is that it's just a contract and it only contains these methods. So that's exactly what an interface is. All right, so now we've got these empty stub methods, stub implementations of these things. Now what we're going to do is write the tests, okay? Yeah, you'll have to go to the recording if you missed that. I'm sorry, folks. But what we're going to do now is going to implement the test. So it's going to be map test, new Java class, map test. Now, does anyone have any idea about how I can write these map tests? Any ideas on how I can write the map test? The simple idea, the idea I was looking for you to answer with, if you're there online, is that we can implement it using by borrowing from the set test, okay? Because the way we do the sets and the way we do the maps is very, very similar, okay? So let's go to the set test. And what we're going to do here is we're going to actually copy all this code over. All right. Here it is. And there we go. Test add. So now we need to convert this to deal with maps instead of sets. And what's the key difference? Maps have values associated with them. And the way we're going to do it is we're going to give a value to each of these things we've added to the map. What's a natural thing? At the moment, we're adding people. So what's something we can add to that as a value? We can add the age. So what we're going to do is we're going to add the age of the person to the map. That's the way we're going to do it. So we're going to change this here. We're going to say refactor this and change this to call it rename hash map. All right, for those of you who missed that, what I'm doing here is I'm borrowing the code that we got from the set over here and using it as the basis for our implementation of the map tests. And the way we're going to modify this, I'm just going to refactor and rename these things. We're going to call it a map like that. Same down here, just do this systematically. Refactor, rename. Like that, and refactor, rename. And refactor, rename. Oops. Okay. So now what we're going to do is going to add to each one of these things here a an age. Okay, so instead of having just a set which has just the people, we're going to have the people and attach to those people an age. Just 1 second. I'm just going to pause again and see if there's anything else I can do to fix up the connectivity. And I think the answer is absolutely nothing. Unbelievably frustrating. Yeah. I'm pretty sure I've just got a problem in my street or something with the internet. Anyway, I'll forge ahead here. Okay, so what we're going to do here is assert true, the map size is 0. Same deal as with the set. I need to change this here to map, 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 and then change this to hash map. And tree map. And now the map, what's the type here? It's going to take in what we're going to do here is we're going to make a map that has the person's name and the person's age. So we're going to have a string and an integer. Okay, so string comma integer. And here, and BST map, sorry. It's BST map. Okay, and we can copy this piece of code here into each one of these so they all look the same. There they are. And and then what we're going to do is add to the map the value. And so what we should, we need to put, the operation for maps is not add, but put. Okay. And so the map should be of size 0 at the start. And then after we put there, we should have size 1. And then we say, if we say to string, we should have Alice, comma 19 as the to string, because now we've got a value as well as the key. And then if we add Alice again with a different value, like 18, then the map should still be that, but Alice will be with an age of 18 now, because it's been overridden by the previous one. All right, and then here we're going to do the same thing with Bob, put, and we're going to say Bob, and give Bob some age, 20 or whatever, not 10, hopefully at university. This is students. And now we should have 2, and it should be Alice, Alice, comma 19, and so 18, and Bob, comma 20. And here we've got Bob, and because it map just like a set doesn't have a guaranteed order. For that reason, we need to just like with a set, need to check for both. Okay, and it looks like my stream is working okay now, but I don't have you on Teams, which totally sucks. Alice, there we go. I've got you back on streams now. Alice, and Alice is 18. So they're the 2 different ways we could have Alice. All right. Someone asked if we can refactor them. I can't, because they're quite different types, and we don't know, and it's actually quite complicated to refactor them. So I can't do this automatically. What I'm doing now, at least not straightforwardly. So now if we add Bob again, and add Bob with a different age, so add Bob with 19, then we should get just the same as this, but with Bob having the age 19 instead of 20. All right, like that. And then we add Cindy, but we don't say add, we say put, like that. And then oops. And what we do here is we'll say add Cindy, do put Cindy again, and we give Cindy a different age, and the map size should still be 3. Okay, so I think that we've rewritten add to deal with a map, and we're now going to do this one here. Hang on, I'm just going to check that why MS Teams is not giving me just 1 minute. Okay, so I believe I can see you all on Teams now, and I believe my stream's stabilized. So now what we're going to do is we're going to do the same thing with null. Okay, we're going to refactor this null thing to work with sets. And so we're going to do a put of null, and it can have an age as well. We'll give it an age of 0. Well, let's give it an age of 1. That should work just fine. And it should print out like this, null, null, comma 1. Remember, null is the key. Java actually allows you to do that. I can't do it. I don't think I can do that. Yeah, let me just see. Someone's asking if I can just do a rename. I'm not sure it'll want me to do that, because it's actually it doesn't usually let you refactor something that's broken. Oh, there you go. I can. It's just still broken, but yeah. Thank you for that suggestion. All right. So now I'm going to do null with 0 stored in there, and then the two strings should be like this: null, comma 0. And folks, while I type all this in, I want to say thank you for tolerating this this very annoying behavior of the streaming. And we should get null here. The string's going to look like this: null, comma 0, followed by bob, comma 20, like that. And or the other way around. Remember that maps, just like sets, don't have defined order, so it could come out in either order. So we have to test for both: bob 20 and null 0, like that. There we are. So that's the two possibilities. We put bob back in again with a different age. Oops, I've got to get the right side of the quotes. It's an integer, like that. And then everything should be the same. Let's just cut and paste this code here and just change Bob's age to 21. And then we should have this test working. Well, not working, but implemented. Now we can add Cindy. We can add Cindy with an age of whatever, and add Cindy again with a different age, like that. Okay, so we now have test add. We've got test add null. And yep. And then we can go here to refactor, rename, put. Okay, oops, I forgot to change this. There we go. And now it's complaining because put needs an argument, which is just fine. And Alice should be Alice, comma 19 or whatever. We've got to give Alice an age, and the map size should be 1, and it should the string should look like this. This is a little bit tedious, I know. It won't be too long. Now what we need to do is not a contains. We're actually going to need to change the name of this method, because instead of contains, what should it be here, folks? What should it be instead of contains? Anyone know? Instead of contains, it will be get. Okay. So refactor this and rename. It should be test get. Contains is the set method. Get is the map method. There it is. And so, yeah, very good. And then what it should say is actually an equals equality of 19, right? Because Alice is 19. And then we should say do a get of Bob, and it should be return null, because Bob's not in there. Okay, so let's just go through this. Okay, so I just changed this now from a contains to see if Alice is in there to a get to say when we get Alice, it should return 19. And then likewise with Bob, I've said get Bob, and get Bob should return null because Bob is not in the map. Okay. All right. Then we're going to put Alice in again with a different age. And then what should happen now is the two strings should still look like that. Alice, comma 18. But the interesting thing is that when we let's give Bob an age. Keep typing that. Mistyping the key. Now what should happen is you can just cut and paste this here. Okay, so Cindy's going to be null this time because, oops. So Cindy will be null. Sorry, folks. Just do this again. Where were we? Alice should be equal to 19, and Bob should be, we do a get of Bob, we should get 19. Oh, Alice is 18, I'm sorry. 18, and we do get of Bob, and we get 19. And then when we do a get of Cindy, Cindy's not there, so it should return null. And I need to change this from a false to a true. Okay, so that's what we should get. Oops, and the bracket's in the wrong place. Okay, so what we're doing here is we're changing our tests to work with maps instead of sets. All right, and then the string should be where's Alice and Bob? I need to cut and paste this. It's too time consuming. Like that. Where are we? There we are. Like that. And Alice is 18, Bob is 19. Correct. There we go. And if we put Bob in again with a different age, Bob and call Bob 20, then now so 21 say, then we're going to change this to 21. Okay, so the two strings should change just like that. And now if we put Cindy in with some age, like that, then these things should all be true and Cindy should be 21. Okay, and the size should be 3. And if you put Cindy in again with a different value, 21, that should be 22. I mistyped that. And then that should be, yeah, no, Brendan, good question. Brendan's asking if there's a reason why I'm using assert true rather than assert equal or assert null. No, in fact, I can do that. Let me do that. Brendan's absolutely right. The reason why I was doing it is just because I'm struggling today, Brendan, because it's incredibly distracting having all the technology breaking right the way down to keyboard mappings. Doing this on a Windows keyboard. Okay, so like that. So that's exactly right, Brendan. Brendan's pointed out that I can do assert null there. Was there another one up here? I think. I don't see it, but if there is, yeah, I can do that repeatedly. He's absolutely right. The better way to do that is to do assert null, and then up here, Bob, we can say assert null, and like that. And the right way to do this is assert equal for this one. Yeah. And then like this. Okay. What have I done here? What's the matter with this? Ah, boy. I'm not sure what's happened here. That should be right. Anyway, let's just go back. I'm sorry, I'm just slightly flustered by everything not working properly. We'll leave it like that. But yeah, I should be able to use that. Linda's pointed out an error here. Bob should be what? Bob should be 19. Very good. Thank you, Linda. Well spotted. And Bob is 19 here, like that. And finally, we're going to do remove. Okay. So what we should be able to do is, okay, we're going to type all this junk in again. We're going to, again, someone said we can just change this to refactor this to put, refactor to put, refactor rename to put, PUT. There it is. And then we're going to add Alice 19. And then the string should be Alice 19, a key value pair, like that. There it is. And then it should be get. When we do a get of Alice, we should get 19 equals string, whatever. No, I don't know what I'm doing wrong there. Let's just say assert true. But we should better use get equals there. Assert equals, but we'll do this instead. And then we should be able to say assert null here, just like Brendan said earlier. Like that. And then when we do the remove, we should be able to remove each of those, and we should get a size of 0. And when we do we should be able to be able to do assert null of get of Alice down at this point. Assert null get Bob, assert null get Alice. They should all be null. Now if we put Alice back in, then the size will be back to 1. Well, oops, I've done another typo here. And I'm nearly done with this test, folks. If you think this is tedious, we're nearly done. And then we need to, the two strings should be like this. Like that. Oops. And we need to, we're going to put Alice back in again with a different value. And that should, again, not make any difference to the size of the set. And Alice should now be 20 because we've overwritten the value of 19 with 20, like that. And now we're going to put Bob in, like that. And now we should be able to test that Bob is alice.get is equal to 20, and get Bob is equal to 19. And we can do an assert null for get Cindy, because Cindy is not in there, so we should get a null when we check for that. And then the size should be that, and let's just cut and paste here again. This is very tedious otherwise. Like that, and like that. I'm just going to make sure I got those ages right. Alice is 20, Bob is 19. Let's just fix that. So 19, Alice is 20, Bob is 19. And then we change Bob's, we do another put here with Bob and change his age to 20, say. And then we can make them both 20 in this line. 20, 20, they should both come up with values of 20. Okay, and then finally remove them. We remove Alice, we remove Bob, Cindy. We should have a size of 1, and the two strings should be Alice and 20. Like that. And if we do a put of Bob, let's just cut and paste this. Assert true dot get of Alice is what? 20. Assert get of Bob is 20. And then when we look for Cindy, it should be null. So we can assert null. Like that. What have I done here? Assert true. It should be an equal. Okay, equal sign. And another equal sign there. Finally, we're going to add Cindy. Give Cindy some age, and we cut and paste all this code here. Save me typing it all again. And the assert true Cindy is also 20. Or whatever age we want, really. But anyway, there you go. And now we're going to make Cindy another age, like. And then that shouldn't change the size of the map. Now, you can see I've gone offline again. And we're going to remove Bob, we're going to remove Cindy. And the map size should now be 1, and all we should have in there is Alice. And Alice is size 20. We're going to put Bob, we're going to put Cindy. We've got to give them arguments again and put them back just like they were. And we should be able to assert there like that. In fact, this whole thing, we can copy this whole thing here. All right, there it is. And now if we run this test, we should find that it is, let's run the test, map test. And it failed, which is exactly what we expect. And here we're testing map, hash map. We should have that true because we're going to implement that map first, the hash map first. Now, what I'm going to do at this moment is I am going to take a very short break. I know I'm back online again. My God, this is so horrible today. What we're going to do is I can see some of you are back online. So let's just keep plowing ahead here. We're going to build the hash map. Frustrating for one of the most important lectures of the year, but I'll just do the best we can, folks, under the circumstances. So, my question for you all, those of you who've persevered and are still online, question for you: what do we need to do to change the hash map? There's one crucial thing we need to do to change the hash map compared to the hash set. What do we need in here? Anyone? What we need in here is a key value pair. So we're going to create ourselves a new tiny little class here. We're going to say class KV pair. If we go back to the PowerPoint, you'll see that each node now, instead of just holding a value, it's got a key value pair. Okay, so we need to we now need to have a key value pair type. So we're going to create ourselves a little class here, which is a key value pair. K key v value, and incidentally, yeah, so we need a key and a value. We need a key value pair is what we need. So we need a key and a value, and we need a constructor for it, which will take a key and a value like that. And then we'll just say this dot key equals key, and this dot value equals value, like that. And what else? Oh, the other really useful thing would be to have a toString method. So it would say at override string toString, and we'll say return. And all we're doing here, folks, is printing out returning a string which has got the key and the value as a pair of strings in parentheses. Okay, so return string. What's happened here? Why is that underlined? Oh, it's gonna be public, of course. Public string to string. There you go. Okay, all right. So now we have ourselves a little class here called key value pair. Now a hash map, instead of being a hash map of type key, is going to be a hash map of key value pairs. And just like so, now what we're going to do is to make this easier for ourselves is go back to the code here we wrote before, hash set, and look at this. And we're going to borrow code from here. Okay, so we're going to take all of this code here, there it is, and put it in our hash map like that. And what we need to do now is, instead of making a linked list of type T, we're going to make a the linked list is going to be of type key value pair, like that. Now I would like to answer Samuel's question there. Samuel's asked, when you have implements map, is map already defined? Yes, map is defined. It's defined in this interface over here. There's map. Okay, and we've got some number of elements, and the type of the element now is the K, right? Because we're going to hash on the keys, and we're going to count the elements, and we're going to have the size method down here. We're going to return elements. Return elements. And what else are we going to do here? We're going to okay, so I think we've got all those preliminaries there. Now what's interesting is I just want to go back to the PowerPoint and show you. There we go. Okay, so now notice that here we have linked lists, and the linked lists are linked lists of key value pairs, key and value, which is what we've got here now. So instead of having a linked list of keys, we've got a linked list of key value pairs, and that's what our table is. It's a linked list. It's a table of linked lists of key value pairs. Okay, and then let's do the first we'll do the put method. Okay, and we're going to again borrow code from the hash set, because it's going to be very similar. So just copy this code here to start with and see how it varies. Okay, I'm doing this for two reasons. One is that it's faster for me to do it this way than type everything out from scratch, which saves you time and it's a little less boring. But the other thing is it illustrates very crisply what the relationship is between a set, which is where I'm taking this code from, and a map, which is where I'm putting the code. Okay, so this is the reason why I'm doing the cut and paste here. So let's just paste that in there. Now it's not going to work, okay, first of all, because there are a number of differences. Now, what's the first thing that's different? Well, we don't have an element. We've got a thing called a key. So first of all, we've got a hash on the key. Someone is putting a key into our map. Okay, next we've got to get the linked list. What kind of linked list is it? It's actually a linked list of key value pairs, right? Not a list of keys. Oops, like that. Okay. Now, if there is no linked list, just as with the set, we need to create a new one. Okay, so if you went to that point in the table, like here, if we went here, there is no linked list, so we need to make a new empty list. Okay, and then what we need to do, this is actually one of the most interesting parts. So I hope the streaming's working for some of you, and some of you are online. In fact, what I'm going to do is going to ask you, what do we do here? This is a really interesting question. For anyone who's online, and I'm really interested to hear what you think we do at this point. Notice that we're using the linked list and we're asking if the element is in there. We don't have an element anymore. So we can do this, right? That's kind of logically what we want to do, but there's a real problem with that. Why can't we do that? Does anyone know why we can't do that and what the problem is? Look back here at this diagram. Now, when it was a linked list of keys for a set, then it was quite simple because we just look for the key and we're done. But actually, we don't have a list of keys. We have a list of key value pairs. Okay, and we're doing a get, so we don't know what the value is. We're looking for the key in a list of key value pairs. That's actually quite subtle. Okay. So this is a very subtle point. Hopefully you've caught what I've said. We're not looking for Apple 350. We're searching for the key, which is Apple. Okay, so we've got to look inside the key value pair and just look for the key. That's an interesting difference. Okay, so the way we're going to do this, we're going to write ourselves a special method that does exactly that. Okay, so we're going to say we're going to look for a key value pair in a list of key value pairs using the key as the argument. Okay. Yeah, exactly. Samuel's got it, and I think Adam too. We're looking in the list of key value pairs for the key value pair that has that key. And this linked list does not contain keys; it contains key value pairs. So we need to write something, and we're going to do that ourselves. We're going to write a function called kv pair find, and then we're going to pass a linked list, just like this. One of these guys. Oops, wrong mouse. One of these guys here. We're going to pass that. Okay, and it's going to and the key that we're looking for, right? And then what we're going to do is going to search through that linked list and see if any of the elements in this linked list have a key value pair where the key in the key value pair equals this key, right? So now what we need to do is we're going to do a for loop. So let's say for kv pair kv in the linked list. So we're going to go through the linked list, go through all the key value pairs here. And then what we're going to do is if kv.key equals what we're looking for, then we know we found a key value pair which actually does have this key. In that case, we return the key value pair. Otherwise, it's not in the list. Okay, so we go through this list, look through each key value pair. If that key value pair has a key that matches the one we're looking for, we're good, and we return that key value pair. Otherwise, we'll return null. Okay? So that little method we just wrote there allows us to solve this problem. So now what we're going to do is we're going to do use that method here. We're going to say find kv pair. Actually, probably what we want to do is something. We probably want to find whatever we want to get back, whatever it is. Okay, so let's just make a variable first. It's slightly different with the set to the map. Kv pair kv equals. We'll say find ll key. Okay, so now that's going to return back the key value pair that we were looking for if it's in the list. Okay, it could return null if it's not in the list. Okay. So now what we're going to do is we're going to say, first of all, we're going to say if KV equals null, right? That means that it wasn't in the list. Then what we need to do is we're going to create a new key value pair. KV equals new KV pair with a key and the value that was given, right? So we've created a new key value pair. We've reassigned KV to be equal to that thing. And now we can add that to the linked list. Okay? So let's just go through this again. We used our special little method to find out if this linked list held any key value pair that had the key we were looking for. And we couldn't just search the linked list because the linked list is looking for key value pairs, not for keys. Okay, so we wrote this little method to do that. Then if we couldn't find any, that means we need to create a new key value pair, which we do, and we add it to the linked list, and now we've got a new element in our set. Otherwise, we must have found it, right? So that means we did find this a key value pair with that key, and then we can what we need to do now is update the value to be whatever was given. Okay, so we can just say kv.value equals value. Right? So there's two cases. One is we don't find it, which means we need to create a new key value pair. The other one is that we do find it, and all we need to do is update the value. All right? Now we need to do the toString. Let's do that because I don't think we can do anything until we've done the toString in our tests. So let's go to toString, and again we're going to pinch the code from the hash set. Here we go. Let's pinch all this code. There's toString, and where are we? Hash map. So we'll just dump all this code here. Okay, so let's just walk through the code. We start off with a return string, which is empty. Then we're going to go through all the buckets. Same thing with the set and the map. They're both going to work this way. Now, the linked list now is a linked list of key value pairs, not a linked list of keys. So we've got ourselves a linked list. If that linked list is non-null, remember it could be null. Let's look here again. It could be like this one. That one's null. But if it's not null, like one of these ones, then we walk through that linked list and we add to the string the representation of each one of those. Now, before we went through and got all the elements, this time we're going to go through and get all the key values. Okay, so we've got the key value pairs. Now, if the string is empty, then if it's not empty, then we put a comma in front. Remember, this is so that the string gets formatted nicely. Okay, otherwise we've got a problem that the string won't have commas in the right places. So that's all that's doing. Otherwise, we add to it, we check to see if the key is null. This is interesting. This code here, what we're doing here is if the element was null, now what we need to do is to check to see if the key value pair is null. And what we're going to do here, we have a toString method here. Oh, here it is. Okay, we've got a toString method for the key value pair, and it should work. If the key is null, it will just print out null. So this should just work. I don't think we need to write this code anymore that we had for the null. So I think we can just get rid of all that, and all we're going to do is add. I don't think we need any of this stuff here. We just add KV. With a bit of luck, that will work. All right, now if things have gone well, what we can do now here is just run our test, our map test. And it didn't work. I was hoping our test add would work, but it hasn't. Null pointer exception. Okay, so let's look here. We've got the error is here. Hash map. Okay, we're trying to hash a null element. Where is it? Presumably this is null. Okay, and now where did that get called? It got called here, line 37. Let's go back and look at the add method and see how we dealt with nulls before. So hash set, what do we do with add with nulls? Add put. That's interesting. If the element is null, oh, I see. Then we just return 0. Okay, so now, did I not type that code in? Let's have a look. That should have worked. So it says here, if the element is null, then do this. Otherwise, why have I got a... Let's see here. Can anyone see the error here? It's saying null pointer exception on line 11. If element is null... Oh, table.length. Oh, goodness gracious. Okay. Why is a null pointer exception? Presumably, we haven't initialized the table. Okay. Now, where did we do that in the set? Ah, we did it right here. We had a constructor. Okay. We didn't write a constructor, so we now have got to write ourselves a constructor. Okay. So let's put that in there. Hash map. We'll write ourselves a constructor. Now it's got to be hash map, not hash set. And it's a linked list, and we just create that linked list. Okay. Now let's run this again. And terrific. We've got test add working. Okay. So now let's move on to we've got, it's called test add. That's wrong. Let's just change the name of that test. It should be test put, right? Refactor, rename. Test put. And here I'll change that to test put null. Okay, let's run things again. All right, now there's one more thing that's not working. We should test put null should work, and it's not. Why is this not working? Aha, it's working here. What's happening is we've got a key which is null, which is interesting. So it's trying to find in that linked list what happens if the key is null. And here, if the key is null, aha. All right. This is interesting. This because I only added the code for dealing with nulls in this lecture. So what we're having here is we've got a case where someone's given us a key that's null. We've actually already, in this example here, the linked list actually does have a key value pair whose key is null. But look, we're calling the dot equals method on the key, which could be null. Okay, so now what we're going to say is that we've got the right key value pair if the key is null of this guy and that is null, or that condition holds. So now we've got to do an or like this, and oops, we'll say if kv.key equals null and key equals null like this. What have I done wrong? Key equals null. Okay, so what we've done now is we've changed the test to see if we found the right element in the linked list. If we're looking for null, the key's null, and we've got a linked list element whose key is null, then we're right. It means we've found the right one. So we return the key value pair. Now let's see if this works. Perfect. So now we've got put null working as well. So now let's do get, okay? And we're going to borrow the code from the set. Do a get here. Where's get? We don't have get, of course. What we have is contains. Yeah, null can't. Griffith noticed on the chat there that null can't use equals. Perfect. That's exactly what I fixed. Just the latency was big enough I didn't see it until after I'd fixed it. All right, so now we're going to use the contains code, which is analogous to the get code. Okay, so now we'll go to hash map, and we'll put in here. We'll just cut and paste this code in here, and then fix it all up. All right, so we're going to whack that in there. So now we're going to find out which bucket it is, and we're going to do that based on the key, right? And then we're going to get a key linked list of key value pairs, kv pairs. Oops, like that. Now, if we got back nothing, that means that that's like here. That's like this example here where we hashed in here and it turns out there's nothing in there yet. That means it's not found, right? So we return null in the case it's not found, not false, okay? But if it's not nothing, then we need to do a find, not a contains, but a find on our linked list. So we call the find method, find, return find, where is it? Find linked list key, okay? Find LL comma, key. And remember, we wrote that code earlier. You may have missed it because of all the problems with the, hang on, what's this returning? Okay. KV pair, KV equals that. So what that's going to do is it's going to search for that linked list and find any KV, or find the key value pair that matches that key if it exists. And now that could be null. And if it's null, we just return null. Otherwise, we return the value of the key value pair. Okay. So now we'll say if KV equals null, if that's true, then we just return that. Return KV. Otherwise, we return KV dot value. Okay. And let's run that and see if that works. And now, what else have we got here? Something's not right. What's the matter here? If it's equal to null, I'll just return null here. Sorry. Yeah, now that should work. And we've still got a problem here. What's the problem? Test get, line 84. Okay, we should get 19 for Bob, but that's actually a mistake in our test. Look, map Bob is 21, so we should have 21 there. So remember, check the test. Sometimes we make mistakes in writing tests. In that case, I made it. Okay, and fantastic. We've got get working, we've got put working, we've got put null working. Now let's go on to remove. We're doing great here, folks. Despite all of our technology problems, we're actually making great progress. Go back to our hash map. Now we're going to do the remove. Again, we're going to show the relationship between the set and the map by taking the code from the set. Where is it? There it is there. And we're going to recast that code into this setting here. Now the first thing we're going to do is hash on the key. And then we get a linked list of key value pairs. Okay. Now, if it's not equal to null, I'm just going to break this code down a bit, because if it's not equal to null, then we do stuff. Okay. Now, the next thing we need to do is we need to say KV pair KV equals find of LL comma key, because remember the find method is going to look through that linked list and find any that match the key. Okay, like that. And now if that is non-null, then we do stuff. If KV not equal to null, then it means we found the thing and we need to go and remove it and like this. We indent there, we remove KV and re-decrement the number of elements. Okay, why did we do that? Let's just quickly recap what we've done here. Okay, we want to remove any key value pair that matches this key. First of all, we hash on the key. We get the linked list that matches that key. If there's nothing there, then we're done. We don't need to do anything. If there wasn't any linked list, again, remember that could happen in this case here. If we got to here, there's nothing there, it means, well, this thing clearly isn't in the table. Otherwise, we use our find method to find a key value pair that matches the key that we're looking for. If it's the key value pair that came back as null, then we don't have anything to do. Otherwise, we go and remove that key value pair from the linked list and decrement the number of elements. Okay, any other questions? All right, yeah. Zhu Yuan was pointing out that the double the operator. Where is it? Where was I doing that? Was it here? I think. Someone was pointing out that was querying about this here and the fact that I'm assuming here that the KV is not null, and that's because I've already tested for it over here. And the reason why it works is because in Java, if this part here evaluates to false, it won't test this part at all. So the fact that this would fail doesn't matter because the if statement has already stopped at this point, and then we call it short circuiting. Okay, so well observed, good point. All right. Okay. Now I think hopefully I answered your question. Now, did we get that finished? I was distracted by that there. Maybe we have. And if we have, we can run this and we'll pass the test. If we haven't, we're not going to pass the test. All right. Excellent victory, guys. We've finished hash map. That's really, really important. You now know how to build from scratch a hash map. Well, we didn't really build it from scratch. We pinched the code from hash set, which is actually really important. We have enough time, believe it or not. I think we have enough time to now do the BST map, which is going to do the same kind of thing, but building from the binary search tree. Okay, so we're going to build the BST mapper up from the binary search tree. And we're going to, again, copy code over from the map, but before we do that, from the set, before we do that, let's copy this inner class here, this little class here, because we need to do exactly the same thing with the binary search tree as we did with the hash table, and that is we need to add in a special class for key value pairs. Again, let's have a look at why. There. So previously we just had the stuff in black, that is the apple, orange, and so forth. Now we have a pair of things. That's called a key value pair. So we're going to write ourselves a little data structure called the key value pair, and each node is going to have not an element as it did for the set, but rather it's going to have a key value pair. Now the key value pair in our implementation is one class. In this diagram here it looks like two separate objects. Actually we're making it one object in the actual implementation, so the PowerPoint's not perfectly representing what we're doing, but hopefully it's accurate enough to give you the key idea. So now let's borrow code from the set. Now I don't believe it. Is that you don't believe that it actually worked? Yeah, no, sometimes I don't believe it either. All right, let's go on and borrow code from the set. If there's something really you didn't believe, tell me what it is. Otherwise, I'm just assuming that you're joking about the get rid of the hash set. We don't need that anymore. And what we're going to do, and we don't need class list anymore. Let's simplify this. What we want now is the tree set. And in fact, I should have renamed this. The name, in fact, I'll rename it right now. Refactor, rename. I want to call this BST set because it's a binary search tree. Right, and I'll do the same up here. I just noticed that. I'd be mean to okay, so I've just renamed those things. Okay, so anyway, let's go to the BST set. This is what we were trying to copy code from before. And what do we have in the BST set? We've got a tree. We're implementing the set using a tree. Okay, so, and we've got this special boolean here to tell us whether the tree contains a null. This is a slightly annoying thing, which I did at the end of Friday's lecture. We're going to copy all that code there, and we're going to just copy that entire tree over. But we're going to have to modify it because the tree, instead of holding elements, is going to hold key value pairs. Right, so let's go back to our map. BST map, there it is. And I'll put all this stuff in here like that. There it is. Now let's walk through this thing and fix it up. These things will go right at the top. Okay. Now, for those of you who've forgotten or weren't here for Friday's lecture, what we're using this boolean for is in the tree we've got a little bit of a problem because storing null in the tree is really problematic. Storing null in the tree is really problematic, and what we do is we just use a boolean to tell us whether there is a null in our tree. Okay, and now, interestingly enough, what we need to do is we need to change this from being a boolean to being something of type v, value, and we're going to change this to call it null value, and we'll call this null, and this will be the value that is stored if someone gives us a null key, and we'll use null to represent that there isn't anything there. If the null, if null was used as a key, this is the value for it. And the reason for this is it's actually really hard and annoying to have null values inside of the tree. Although now I'm thinking of it, I wonder if it's different. Actually, we don't need to do this. Sorry, I'm thinking on the fly here, folks. I think we don't need to do this because the key value pair will take care of it. Let's see what happens. I'm gonna hope for the best here and see what happens here. Okay, so now we've got ourselves a binary search tree, and what's in here, instead of an element, what we have, oops, this is moved a whole lot of code here. We don't want this like this. Get rid of that. Get rid of that. Get rid of these things here. Okay, so this is our binary search tree code, which we pinched, and what we're going to have here is the element that is a KV pair. So I'm going to rename this, refactor, rename, and we'll just call it KV. Right, so each node in the tree is now going to have a KV pair, and we change its type to be KV pair, like that. Okay. Now we want to add something. What are we going to add? We actually adding a KV pair rather than adding an element. Like that. Remember, what we've got here is an inner class, which is a tree data structure. And we say this.kv. So first of all, we see. So let's walk through this. All right. So what we're doing here is we're going to add this KV to our tree. First of all, we check to see if the KV on our node of the tree is equal to null, and if it is, we can make it equal to KV. It means we've hit the end of a node with nothing on it. We can make its child be this KV. Okay. Next, if KV, this KV that we're referring to actually equals the one that we're trying to add, we don't need to do anything because it means that this thing's already in the tree. Okay. Next, we need to check to see what the hash code is, but this is important, folks. So if you're still online, this is something very important here. We're not going to look at the hash code of the KV, but rather the hash code of the key of the KV. Okay? So we need to look at the hash code of the key of the KV, because we don't want to sort according to the KV pairs, but rather we want to sort according to the keys. So what we need to do now is like this, kv.key.hashcode, and then we say this.kv.key.hashcode. Okay, like that. And then that sends us left or right. And we're going to have to do something interesting with the null here. This is all right. Now, if the tree on the right is null, then we create ourselves a new tree, and we add this KV. Otherwise, and then we add this element to the tree. We add it recursively. Okay, so we call this method recursively. Okay, and then likewise for the left, and we'll add it recursively here. Okay, so the one thing I haven't done is this fix me here. We've got an interesting case here with a test null. I think that will break with a test null. Now we want to add a subtree. This should just work. I think there's nothing changed here. The fact that the KVs doesn't make any difference. Now we want to do a find. This is interesting. What we want to do a find on, I assume what we want to do a find on is we want to look for the key rather than look for the KV pair. Okay, because we don't know what the value is when we're doing a search. We're always searching based on the key, like that. Okay, so now what we need to do is again, we need to check deal with the null. Let's put a fix me in here. Okay, if this.kv is not equal to null, means the node that we're at is not equal to null, and the element is not equal to null, that is, and the key is not equal to null, then if they're equal, we found it. kv.key, we're comparing the keys. Okay, if this KV is equal to null, is not equal to null, it means there is one here, and the key is not equal to null, then if the key on this node is equal to the key that we're looking for, oops, like that, then we found it. Okay. In what circumstances would you even have a null key? That's a good question from Adam. Adam, I don't have a quick answer to that, but in fact, it was only recently that I noticed that we weren't doing it. We weren't supporting that, and Java actually allows you to have a null key. So goodness knows why you'd want to have a null key, but the thing is Java does actually support this. We could just get rid of that if we wanted to, I suppose, and just not support it. But that's part of what a set normally does in Java. All right. Now, see, other people in the chat can try and think of examples of where that would be a good idea. I don't know what they are. So now, if the element.hashcode is okay, so now what we need to do is we're not looking at the element, we're looking at the key.hashcode is greater than kv.key.hashcode. Okay, so again, we're looking at the hashcode of the key, not the hashcode of the kv. Okay, then we go left or right. And again, we're going to do a find, and the find's going to be on the key. And find, again, is going to be on the key. And we don't need to do a fix me there. That's all working. Now, this I think will just work, I hope, because what we're doing is a toString on the tree, and it will just do a toString on the KV, which already does its nice little parentheses and everything. So touch wood, that will just work. All right, now let's look at the put method. Let's see if we can make this work. Let's go to the hash, where is it, BST set, and go to the put. Where is it? Right down here. And again, we're going to ignore the null case to start with, which complicates things greatly. We're just going to ignore that. BST map. Get rid of this whole thing for the minute. We might have to come back to that. Now, if the tree that we've got is null, then we need to create a new tree like this. Otherwise, now what we need to do is we need to try and add, let's look at what the add method does. We add it. Right. Okay, let's look at what this code is doing. If we're trying to add the KV pair, if we've got it, so it's going to return null if it couldn't add it, okay? Okay, so let's try and add it. So we're going to create a new key value pair. KV pair, KV equals new. Well, the other way you could do it is to search, I suppose. We just do a search. We do a find on the key. All right, so let's just try that. I'm changing this code as I go along here. If tree.find key, that means we already found it, right? If we already found it, then we're just going to update the value. And what does find give us? Does it give us the KV? It does. It returns a KV. All right. So it returns a KV. So what we need to do is we're going to say if okay, we're going to try and find this. Okay, let's go back up here and look. So to make sure this code makes sense here, where's the find? Okay, so find is going to go and find, look for our key, and it will return the, it will ultimately, if it finds it, it will return the node that has the key value pair that we care about. Okay, so if we do that and the answer is non-null, if t is not equal to null, that means that we found the one that we're looking for, and then all we need to do is update the value. Okay, so then we say t.kv.value equals value. Right, so we just update the value. If we didn't get null, if it returned null, then that means this thing wasn't even in the tree. So then what we need to do is create a new key value pair. KV pair, KV equals new KV pair with a key and the value, right? And then we just say, oops, value. And then what we're going to do is we're going to add that key value pair. We just need to add it now. We just say tree.add KV, because we already know it exists, and we increment the number of elements because we've added something to the tree. Okay, so there's the two cases. We're going to put something in the tree, and and first of all, we just check to see if there even is a tree. If there isn't a tree, you need to create one. Next of all, we go and look to see if this key is already in a key value pair that's in the tree. And if it is, then all we need to do is update the value. If it isn't, then we need to create a new key value pair and add that key value pair to the tree. Okay, and for now, size should return elements like that. And we might be able to test this. Let's just try and test map test. Change this thing at the top here to test for the BST map. Change this to false. And then we'll run this test. And with a bit of luck, we might have add working. Let's just see. We didn't. Let's not even called add. It's called put, of course. What happened here? Test put. What did we get back? We didn't get that. We got something else back. Apparently, we got the size right, but we didn't get the right thing. Let's see what it came back. All right, that should print it out. Now, I realize I've got 3 minutes left before the end of class. I'm not quite going to finish it on time. Oh, okay, so that's really simple. Okay, so the toString didn't work, but that tells us that we haven't implemented toString. So that should be very simple to do. That's probably because we forgot to do this. Where is it, toString? We didn't implement this. So let's just cut and paste this and put it into the BST map down the bottom here. Now we can ignore the null. There we are. With luck that will work because we already wrote I think the toString for the tree. Yes, the put worked. Okay, so that's great. Put null didn't work. We'll come back to that in a minute. We will. What happened here? Let's see if we can fix this. Right. Haha. Look where it failed, folks. It failed right where I had this fix me because I knew we were going to run into a problem here. Let's try and fix this. So what we're trying to do here is we've got nulls in here now. Okay, and we need to know whether to go left or right when we're traversing the tree. Now the key that we're looking at could be null. Okay, so all we need to know is always go in one direction for null. Okay, it doesn't matter which way as long as we're consistent. It just needs to be deterministic. So we can always place nulls on the left or the right. It doesn't matter. So we can just add something like this, I think. kv.key equals null, or that, or all the other stuff, then go that way. We could just as easily say not null. Either way, as long as we always deal with null keys the same way when we're doing the search, we should be good. Okay, and we're going to have to do the same thing for the find as well. Same thing here. Yep, if key equals null, is that the right direction? Key equals null. kv.key equals null, right? Then we go to the right. Is that right? kv.key, we go to the right. Okay, so hopefully that will fix that. It may still not work. Some of it worked, but not all of it. Okay, this one didn't work. Okay, the size didn't go to 1 for some reason. Okay, what I'm going to do is I'm going to skip past this. We'll come back to this in a minute if we have time, because I know you all want to finish. And what we're going to do is get the get working, which should be fairly simple because we've just hit time. Unfortunately, this lecture was horribly delayed by a whole bunch of technical things, but I'm going to try and get the remove and the get working, which should only take me a few minutes, I think. And so if you're able to keep watching, then great. If you're not, then no worries. I understand that completely. And I encourage you to come and watch the video later. But we'll try and finish this all off now. So we're going to do contains, which is equal to get, which is the equivalent to get. Okay, BST map. So the get here, we're going to use the same pattern. We're not going to, we don't going to do that. Instead, what we're going to do is, if the tree is null, then of course we return false, right? Well, we return null actually. What that means is there's nothing in the tree, so what you're looking for can't possibly be in there, so we return null. Otherwise, we do a find of the key, and we just return whatever came back dot kv dot value. Actually, we've got to make this a little bit more fancy. All right, so now what we're going to say is kv pair. We're going to do a find kv equals, do a find, tree.find.key. Okay, so we're going to get this back. Now, if kv equals null, what happened there? Oh, BST. Okay, so we've gone and had a look. If the thing that came back, what does it return? A null tree. We're going to do the find. Let's have a quick look here. It returns a null tree. Okay, so if t equals null, means we got nothing back, then we return null. Otherwise, we will return t.kv.value. Okay, and get rid of that line there. Let's see if that works. We'll run this. Someone's asking questions on the chat. Oh, I've just gone offline again. All right, the put worked and the get worked. Fantastic. So now we're just going to do the remove, and we'll do the same thing. We're going to go to the set here. So where's remove? And we're going to follow the same pattern, but we're going to ignore the null for now. Just grab this. And BST map, and we'll put this in the remove. Okay, first of all, we're going to find the root of the tree when we look for that key. And then we're going to have a left and a right. And now what we're going to do is we're going to set the kv to null if we found it. Okay. So if it's not null, that means we found it. And we set the root to null. We reduce the number of elements. We set the left to null. We set the right to null, and we add it. So with a bit of luck, that will work as well. Fantastic. So the only thing that's not working now is is this one here, the put null. There's at most one null. So now let's just see if we can. So we passed one test. We passed 3 out of 4 tests. So we're only failing one test here. So let's just see where we're failing this. We're failing this one here. Put null 0. I see. So in this case here, we've already put null in there. Now we're putting null in again. And when we put this in again, the size should be 0. So this is exactly the question someone's asking. Can we put 2 in there? And the answer should be no. I wonder what the size is. I bet the size here is 2. Let's have a look here. S out. Oops. Map.size. I bet the answer is 2, which it shouldn't be. Because I bet what's happened is we've got 2 nulls in the tree, which would be really bad. Yeah. Okay, so it printed that out twice. It's added null in twice, which is just the question that someone was asking on the chat just now. So let's go and make sure that doesn't happen. Why would it do that? Let's just step through this. Okay, we want to add something. We're adding in null twice. We're doing a put. So we put the key. All right, so we try and find it, but apparently it must be returning null here because it's incrementing the elements here. So it mustn't be finding it. So let's just see here what's going on. Tree find key. Where's the find? Okay, so the key's null, remember? Here it doesn't allow the key to be null, but we do need the key to be null. We need to allow the key to be null. Okay, so this could be a problem. Let's just get rid of that for now. Let's see if that's not breaking other things. Now we've got a null pointer exception. All right, let's see what's happened now. Okay, we're doing an equals on key. Okay, so what we're going to have to do here is say if this dot kv dot key equals null and key equals null, then we found it. Okay, or that. All right, so we need to do a slightly more elaborate check. Else, if the key is null, okay, so we just had to add that extra check in there. Is that enough? No, still got a problem with a put null. Null pointer exception here now. Why is that? Oh, sorry. Oh, sorry. If the key is null, okay, our logic's wrong here. It's doing this if okay, this is a little bit more complicated than I expected. Okay, so we've found it if the we've got to make sure here that we don't keep searching if the key is null. The key we're looking for is null. So say not equal to null, and like that. Okay, so we've got to do one or the other. So if the key is null, then that has to be true. Otherwise, if the key given wasn't equal to null, then that's all right. We can't do this equals if the key is null. And we've still got an issue here. Issue is on the same line again. Line 55. Null pointer exception happening when we call this code here, the find of the key, and we've got a key that is null. No, Brendan asks if the key KV is null. If you have a null key, it shouldn't be. It should have a null value. It should have just a null key. The KV shouldn't be null. Okay, that's important. If it is, then we're in trouble. But that shouldn't be true. Okay, so so this dot KV is not equal to null, that we do this stuff. Okay, now if the KV, all right. Maybe it's going to be cleaner if I just write it like this. If key equals null, then do some stuff. Then do the search one way. Otherwise, do the search the way we had it before. So if the key is equal to null, then what we're going to do is we're going to say if this dot kv dot key equals null, then we found the right thing. Okay, so then we return this. Okay, this. Otherwise, else we return the null should always be on the left. Okay, we keep traversing. Sorry, on the right. We return right.find.key. Right.find.key. Find key. Okay. If right's null, then we return null. We return null. Otherwise, we traverse down there. Else, we do all this stuff. We can get rid of all this stuff. How was it before? It was this.kv. Oh goodness, I've lost track of what it was before. So let's go back to this find here. Right, we're just doing equality. Okay, so just that equality there, BST map. It should just be this here. Okay, if this.kv.key equals key, then it's found. Okay, so hopefully that has not broken everything. And now I need to do a close parentheses here. There. Let's run this. All right, still not working. So Griffith asked, don't you also need to check if kv.key equals null? But I'm not sure where you mean. I probably do. Okay, so hang on. Things have gotten further here. BST map. Okay. All right. So here, where. Okay. So now we're putting stuff into the tree, but we've got null elements in there. So the problem we're finding here is different. What is the key that we're looking for? We're looking for Bob. Okay, we're looking for Bob, but we must be hitting a null key. Okay, in this case, oh, I see. So the error was on that line there. I guess it was on this line here. And in this case, the key is null. So I still have to go back and put that fix in I had before, right? So if the key is null, then it mustn't be the case because this key is not null. So we say if kv this dot kv dot key not equal to null and that. All right, let's run it. Still not working. Oh my. So let's just check this now. We're still in the same place, still there. Now we're trying to add this key value pair. And the way it does the add is it's first of all looking through here. If this dot kv equals kv, then otherwise if the kv dot key equals null, then go through here. The problem is again, we've got to check the case where the this dot kv equals null. Okay, so if we're trying to add null, we go to the right. If the and we're going to say here this dot kv dot key is not equal to null. All right, that's a problem there. Making more progress. Still not quite done. Okay, now we've put Bob in there, and we've added Bob, and we've still got a problem with the number of elements. Why is that? We've added Bob in twice. It seems like it's not finding Bob in the second time, so now Bob's put in that tree twice. I bet that's what's happened. Yeah, it's got Bob in there twice now, which is a mistake. So that presumably means that this that when we go to add it, it's going the wrong way here. Have I got that the wrong way around? So if the key is not equal to null, and that's the case, then you go to the right. I'm going to have to leave it at here because I know that you're all waiting. It's all over time. I'm going to finish off with the bio, and I will debug this offline and get back to you. Let's move through here to the bio. The bio today is actually a really cool one. It's Shafi Goldwasser. Shafi Goldwasser is a remarkable computer scientist. Not only did she win the Turing Award in 2012, but she twice won the Gödel Prize. She's a cryptographer and a theoretical computer scientist. One of the cool things she did is zero knowledge proofs. They are a really interesting idea. The idea of a zero knowledge proof is very important to cryptography, but it's this idea that you want to demonstrate that you know something without demonstrating that knowledge itself. Okay, that sounds pretty tricky, but okay, so I know a thing, like I know a secret thing, and I want to demonstrate to you that I have that knowledge without actually revealing that knowledge. And I took this straight out of Wikipedia, but here's an example of it. So imagine we've got Alice and Bob here, and Alice, and we've got this cave, this special cave, which has one entrance, right, and a split, which goes the A path and the B path, and between them, there's this wall, this magic secret door, okay? And the only way to get across this line here is if you have the magic password, okay? Now, Alice is trying to convince Bob that she knows the password, okay? And if Bob stands here, he can't see her enter the password. So the way she can prove to Bob that she has the password is to disappear down A, and then Bob can say you need to appear through through A, and Bob can say okay, you need to appear through B, and then she can only possibly do that if she has the password. She does not need to tell Bob what the password is, but she can prove to Bob that she has the password by virtue of her ability to come out through either A or B, regardless of which one Bob asks and regardless of which side she is in, because she knows that that secret knowledge. Okay, this is a pretty interesting idea. It's part of Shafi's work, and I encourage you to look it up on Wikipedia or somewhere else, and you might find it's quite I think it's quite an interesting thing. And with that, we'll finish up, unless there's something. Oh, someone's got one last suggestion on the code, and gee, I'd love to fix it. So let's just see if he's right. It's Brendan. He says, Griffith says, don't you also need to check if kv.key equals null? Yeah, maybe, but where? And then finally, Brendan says line 32. Line 32, here's our BST map. Line 32. If we add here, we're doing an add. Oh, I see. This is about whether to go left or right. Don't we have to check to see if it's this.kv.key? No, that's just seeing if we have the entire thing already there. So that I don't think is wrong. Okay, or is it? Or is it? That's a good question, Brendan. Let me just check that. If we want to add something to the tree, we've already checked to see if this is in there. So we're only adding if it's not already in there. So I think that's correct. I don't think that's the problem. Okay. All right. No worries. I don't think that's the problem here. I think in fact, what I'm going to do now is I've kind of finished the Shafi Goldwasser thing. I'm just going to sit here and debug this. You can all just leave if you like, or you can watch me try and debug it. Okay, and try and help me debug it if you wish. Otherwise, feel free to go. All right. So let's just get here and see what's going on. I hadn't written code before for dealing with a null, so we're kind of in uncharted waters, which makes it kind of interesting. If you're feeling overwhelmed, you're very welcome to go and just catch this up on the video later. But for now, I'm going to try and make this thing work. There we go. Okay, and exactly as I expected, what's happened here is we've got Bob getting in there twice. Yeah, no worries. Sorry that everyone had to tolerate the horrific technical problems. I apologize for that. Not much I can do about it, unfortunately. I can see my bandwidth here just fluctuating wildly. I have no idea why. All right, so Bob's in there twice. Bob should not be in there twice, all right? So when we've gone and added Bob the second time, it should just change the value, but it's not. Again, it could be what Brendan's saying. Let me just go back to what Brendan just asked. Okay, so let's just go to what Brendan asked. Okay, so Bob's in the tree, right? And this add should only get called after we've checked. Let's just check what happens down here. Let's have a look. Do a put, okay? So now we're going to put, and we're putting Bob in for the second time. So we'd first do a find for Bob, okay? Now, for whatever reason, we're getting a null tree back when we search for Bob, okay? So that we must be getting a null tree back from when we search for Bob. Otherwise, because that's the only way we create a new k value pair. So we must be getting a new a null tree back at this point here. Okay, so that's presumably the problem. The problem is when we're looking for Bob the second time round, we're not finding him, and so we're adding in the tree. So this find method is not finding Bob correctly. Okay, so and notice that the null is on the right hand side of the tree. Okay, so the null is out there, and we've added Bob twice to the left. Okay, and which one did we add second? Let's have a quick look at the test, map test. The second one is 21. Yeah, so we've added Bob there, and then we've added Bob there. So we're not, we've for some reason we're not doing that. So we're finding the null and just stopping at that point. And null is probably the one at the top of the tree. Okay, so let's just check this. Okay, so we can go to this code again. What are we doing? We're saying put. We're going to find of Bob. Okay, we go up here. Now Bob's already there, and it's just below the null on the left of null. Okay, so now we're find, and we say find Bob, and we say if this.kv is not equal to null. Okay, if this key is null, which it is in this case, the top of the tree has null there. And then if if Bob, that's this key. So no, we're not adding null, so it's okay. So we should come down to here. Now we say if this.kv is not equal to null, and okay, so we're not, which is okay, and this.key equals key, then okay, so we shouldn't be in that case, because that would only be true if we're actually searching for null, so that should be okay. Otherwise, if the key that we have is null, which it is because we're at the top of the tree, which happens to have a null key in it, and the hash code, then it says we need to look to the right. Ah, that's the wrong way around. Okay, that's the wrong way around. So what we can do is change the logic here to work in the other direction and change the whole sense of this, okay? Because what we're trying to do here is we're trying to protect this piece of code from being executed in the case where okay, so hang on, what we want to do is we want to go down this, we want to go to the right if the hash code is greater than the one in the tree. That's when we go down to the right. But we also want to go down to the right, but we don't want to go down the right if that key is null. Okay, that's when we want to go to the left. Okay, so that's our problem. So really, the one way to do this is to change all that logic there, so that we've got two choices. One is when we add the key to the tree, we add it to the left rather than add it to the right. Let's just see how we're doing out up here. Okay, we're trying to add one. Where do we add it? If a key is null, then we're adding it on the right. Okay. Oh, I see. What this is doing is this says if the key is that we're trying to add is null, then put it on the right. And if this key is not null, aha. Okay, so in this case here, what we're doing is we're saying if the key is not null and that stuff holds, then put it on the right. But in the other case, we're doing the other way around. So this is the problem. So I think the right way to deal with this is to change this like that, and then we just change all the sense of this around to left and right, left, left, and right, right. Okay, and what that's going to do, the only thing we didn't change was this. So that's going to change the sense of whether to look on the right or the left if we get to a node with the key equal to null. And hopefully, yes. All right, we fixed the bug. Hopefully you understood that. Let me just recap it in case you didn't, if you're still there online. We fixed the bug. What was going on here? This is a little bit tricky, okay? This code here, we can't execute that code correctly if this thing is null, because we get a null pointer exception. So we have to have this code in front of it, okay? But the way we had it before was it meant that we were forcing ourselves to always look on the right, but we actually need to look on the left because Bob was actually on the left, because up here we're always putting stuff to the left of the null node. And so by flipping this around, just flipping the logic around, changing that from being greater than to less than or equal to, I change all the logic but still keep this protection in front of the null pointer exception, and then it works. Okay, hopefully that makes sense to you. Sorry today's lecture was such a pain with all those technical issues. I'll upload the video soon, and I hope you all have a good week. So thank you for your patience.